So beginning at the smallest unit of data is a bit. A bit can be in one of two states, 1 or 0. Bits are regularly grouped together into segments of different sizes, depending on the job they do. The size of the group would depend on how much data is needed. Needless to say, the more bits, the more data. Terminology for some of the common data unit sizes are shown here. The bit, short for binary digit, is the smallest, most fundamental unit of data. A nibble, made up of 4 bits. The byte is made up of 8 bits. The word, made up of 16 bits. And the double word, made up of 32 bits. I want to quickly show you what data sizes are supported on the programmer calculator and where to change that. You see, if we click here, we can change the size, and it goes as small as 1 byte. And we set a byte as 8 bits. So in binary mode, we can enter 1 and do it 8 times. There's 8 bits. But if I try to enter more digits, they're not accepted. 1 byte, and that's all. But I can change the size to word, and now you see 16 bits. Change it to D word. That is short for double word, and now the limit is 32 bits. The programmer calculator goes up to Q word, and that's a quad word of 64 bits. But I don't think you will see much of that in regular PLC programming. That brings us to the basic numerical data types. A data type will make use of the different size data units. Data units can only store a series of 1s and 0s, but there is a code where numbers can be expressed in different formats with a varying range of values depending on what data type is used. The basic data types, sometimes called the atomic data types, are simple data types consisting of one piece of information. The basic data types include Boolean, integer, and floating point. When programming PLCs, especially when performing mathematical operations or moving data, we want to select a suitable data type. So we need to consider the range of numbers in use. If you are programming a PLC that controls a machine that packs 24 bottles of soda pop in a case, you'll want to know how many bottles starting at 0. So the range is 0 to 24. There's a data type that's suitable for that. You must also consider, will the selected range extend into negative values? For example, you're programming a thermometer display and you need to show temperatures as low as -10 and up to 100 degrees. You are working with negative numbers, and there's a suitable data type for that. And then there's this. Are floating points required? That is to say, if you are using numbers with fractional values that are expressed with digits that extend to the right of the decimal point. Let's go back to the thermometer example. The specification has changed. Now you need to display the temperature variations as small as 0.01 degrees. The current temperature is -4.31 degrees. Now you are working with numbers where a floating decimal point is required, and there's a suitable data type for that. When working with numerical data, it's important to select a suitable data type, or else the data can be corrupted, and you don't want that to happen. The data types that are available to the PLC programmer are defined by the PLC manufacturer. The data types that are already part of the PLC designs are known as predefined. Exactly what data types are predefined or how they are named will differ depending on the manufacturer. So, of the different data types, let's start with Boolean. A Boolean data type requires only 1 bit and can only be one of 2 different states, 0 or 1. Generally, 0 is representative of an off or false state, and 1 represents the on or true state. And that sums up the Boolean data type. And then the unsigned integers. Unsigned integers are whole numbers. Whole numbers begin at 0 and go up from there, incrementing by one whole number at a time. There is no fractional component. There is no floating decimal point. Whole numbers do not extend below 0 into negative number territory. Therefore, unsigned integers are capable of handling positive, non-fractional numbers only. To remember the term unsigned, you can think of it this way. There is no need to put a positive sign or a negative sign in front because we know only positive values are possible. So this integer remains unsigned. Since we are dealing with whole numbers only, the code for unsigned integers is not that complicated. We already know how to convert from binary. The range of an unsigned integer is limited by how many bits are assigned to the particular data type. For instance, the 8-bit unsigned integer. This data type occupies 1 byte. Remember, we talked the different sizes, and a byte is 8 bits. Converting from binary, we can see that 8 bits could range from a value of 0, when all bits are at 0, to a decimal value of 255, when all bits are at 1. So if we need to manage a number greater than 255, then there is the 16-bit unsigned integer. This data type occupies 1 word. A word has 16 bits. Converting from binary, we can see 16 bits could range from a value of 0, when all the bits are off, to a decimal value of 65,535 when all bits are on. So, in comparison to the 8-bit unsigned integer, you see a greater range of numbers. But what if we need to work with positive and negative numbers? We have a data type for that, called the signed integer. The signed integers are capable of handling positive and negative numbers. They will extend below 0 into negative values. But remember, integers do not work with fractional values. They have no floating decimal point. We will take a look at how the signed integer is coded to handle numbers above and below 0. The range of numbers for the signed integer will be limited by how many bits are available in the data sizing. Let's look at an 8-bit signed integer. And we start off with 1 byte, 8 bits of data. We know how to convert from binary, and we know that 8 bits could range from a value of 0 when all bits are 0 to a decimal value of 255 when all bits are at 1. But signed integers need to express negative values as well. So how are we going to do that? I want to show you this bit right here. This one that is most to the left. It is considered the most significant bit. And that stands to reason. Since beginning at the very right, each bit to the left has a higher magnitude than the one before. I can show you, I can enter 1 on the programmer calculator and then enter zeros, and that shifts the 1 from the right to the left. And you can see the value of each bit up to the most significant bit with a value of 128 decimal. So it is evident that this is the most significant bit. And by the way, it is commonly referred to as the MSB. So normally the MSB is worth 128. But we do something special for the signed integer data type. What happens if we flip this and say the MSB is worth negative 128 if the bit is set to 1? This gives the data type the capability to express negative numbers as low as negative 128, and we still have the bits to the right of the MSB to express positive numbers. Consider the diagram labeled integer 8-bit signed. The byte at the top of the diagram has ones in all the 7 bits to the right. This converts to a decimal value of 127. So we know the 8-bit signed integer can represent a number as high as 127. The byte in the middle of the diagram has all 8 bits set to 1. We know the MSB has a special purpose and is worth minus 128. So add the first 7 bits worth 127 to minus 128, and the result is minus 1. The byte at the bottom of the diagram has the MSB set to 1, and the 7 bits to the right are all 0. The result is minus 128. We know that the 8-bit signed integer can represent a number as low as minus 128. Regardless of the other bits, if the MSB is 1, then we know the value will be a negative number. I want to show you quickly that the programmer calculator works with signed integer. We left off here with 8 bits on the display to show the decimal value of 128 when bit number 8 was set to 1. If this works with signed integer, then why is this not a negative number? Well, there's a reason. It's the data size. The calculator defaults to Q word, and that is a quad word of 64 bits. So I could enter 64 digits before we get to the MSB of a Q word. If I set the size to byte, you see now that the number is negative 128. So there's something else to consider here. I'm going to clear this and put in a value of 127. This is the upper limit for positive numbers. So what happens if I add 1? I get minus 128. Since when does 127 plus 1 equal minus 128? When I exceeded the positive limit for the 8-bit signed integer, it went into overflow. Overflow is the kind of problem you will face if you do not choose your data types carefully. So to summarize the 8-bit signed integer, the data type is 1 byte long. The MSB is assigned a value of negative 128 if the bit is set to 1. The range it can handle is negative 128 to 127. So what if I need to work with numbers larger than 127 or lower than negative 128? Here is the 16-bit signed integer. It handles positive and negative numbers in similar fashion to the 8-bit signed integer, but with a larger data size. This data type occupies 1 word. A word is 16 bits. With more bits, it can manage a wider range of numbers. The MSB is assigned a value of negative 32,768 if the bit is set to 1. So the range it can handle is negative 32,768 to 32,767. So here is a 32-bit signed integer. The data type is 1 double word. A double word is 32 bits long. Some PLCs have to join 2 16-bit words together to generate this data type. Joining the 2 words together works just fine, but as you move on to learn programming and word addressing, you will discover that 2 word addresses will have to be reserved for a 32-bit data size. In comparison, PLCs with a 32-bit data bus can handle the double word just as easily as they would a normal word data type. The 32-bit signed integer is similar to signed integers that we've already talked about, but with more data bits to handle a much larger range of values. The MSB is assigned a value of negative 2,147,483,648 if the bit is set to 1. The range it can handle exceeds 2 billion to the negative and more than 2 billion to the positive.